Welcome to this video on the synthesis and evolution of tungsten carbide. We will explore how this material has moved from atomic lattices to high-entropy alloys and advanced additive manufacturing. Tungsten carbide is a multi-billion-dollar industry, with global production reaching 60,000 tons per year. The core paradigm remains a two-phase composite, blending ceramic hardness with metallic ductility. We are now seeing dual disruptions from additive manufacturing and high-entropy alloys, alongside a strong move towards sustainable recycling. The story of tungsten carbide is one of continuous refinement. Starting as a laboratory curiosity in 1893, it saw a breakthrough in the 1920s with cobalt binders. Later decades focused on microstructural tuning, leading to today's frontier of additive manufacturing and the push for cobalt-free, sustainable solutions. The production pipeline transforms precursors into precision powder through calcination, hydrogen reduction, and carburization. A critical aspect of this process is the carbon balance. A deficit leads to brittle phases, while an excess creates free graphite, both of which compromise the material's structural integrity. The microstructure consists of a hard ceramic phase of tungsten carbide and a tough cobalt binder matrix. The ceramic provides exceptional hardness, while the cobalt binder ensures the necessary fracture toughness and ductility. Grain growth inhibitors are used to pin boundaries and prevent abnormal coarsening. Engineers face a core dilemma, balancing hardness and wear resistance against fracture toughness and impact resistance. Key metrics include contiguity, which measures grain contact, and the mean free path of the cobalt layer, which is a primary determinant of a component's ability to survive impact. The manufacturing cycle involves milling, granulation, compaction into a green body, liquid phase sintering, and post-processing. A key mechanism here is Ostwald ripening, where fine grains dissolve and reprecipitate to drive density above 99.9%. To bypass the limits of conventional sintering, advanced methods like Spark Plasma Sintering and high-temperature, high-pressure processing are used. These techniques suppress grain growth and enable the creation of nanostructured hard metals or binderless tungsten carbide with ultimate hardness profiles. Additive manufacturing presents unique challenges for tungsten carbide. While processes like laser powder bed fusion offer geometric freedom, they struggle with thermal cracking and material degradation. Alternatively, binder jetting avoids thermal gradients, but requires significant post-processing to reach full density. The industry is currently facing a, quote, cobalt crisis due to health regulations, supply concentration, and performance limitations. This has accelerated research into alternative chemistries, including nickel and iron binders, binderless options, and the highly promising field of high-entropy alloys. High-entropy alloys are defined by their complex blends of multiple elements. They leverage the quote, effect to achieve superior properties and sluggish diffusion to inherently prevent abnormal grain growth. These alloys are central to the goal of developing cobalt-free, high-performance binders. Tungsten carbide's dominance is driven by its exceptional properties. It offers massive compressive strength, superior thermal conductivity, excellent abrasive wear resistance, and high-temperature oxidation survival, making it the industry standard for precision tooling. Different grades of tungsten carbide are suited for different roles. High hardness is prioritized for tools like micro drills, while applications like mining bits require higher fracture toughness. Coated and specialized compositions serve the demanding middle ground of metal cutting and aerospace components. Sustainability is critical for this industry, with 35 to 40% of global tungsten carbide already sourced from recycling. Two primary routes, the zinc process and hydrometallurgy, allow for the efficient recovery of raw materials from scrap, supporting a circular economy. In conclusion, the future of tungsten carbide lies in binder innovation, advanced additive manufacturing, microstructural engineering, and the integration of AI. It is no longer just a pressed powder, but a highly tunable, multi-scale engineered composite.